Okay, so I'm going to do problem 49 from chapter 7. And in this, we have a scenario where there's two springs that each initially start at this length L. Then a mass is pulled a distance x out, stretching the springs. So for this, we have the initial length is L because they both start just vertically. And then the final length is L squared plus x squared, the square root of that. Because from the Pythagorean theorem, this is L, this is x, and the spring is the hypotenuse. So then the force from a spring is equal to negative k times the change in x. So we know that's negative k times the final length minus the initial length. However, from here we could see that the springs, when they pull, they have a vertical component and a horizontal component. However, the vertical components will cancel out because one's upwards and the other is downwards. So we only need to worry about the horizontal force. So if we label this angle as theta, we could take the force from one spring and multiply it by cosine theta. And cosine theta is equal to adjacent over hypotenuse, so that would be x over root x squared plus L squared. So then multiplying those out, and then simplify, and then moving the x to the k, and dividing this portion by root L squared plus x squared, gets us negative kx times 1 minus L over root L squared minus plus x squared. Then lastly, because there's two springs, we have to multiply that horizontal portion by 2. So it's negative 2kx times the quantity of 1 minus L over root L squared plus x squared. And then for B, we need to find the potential energy of the spring. So we know that the potential energy of a spring is 1/2 k times change in x squared. So this would be 1/2 k using the final length minus the initial length squared. So then expanding out the squared term gets us 1/2 k L squared plus x squared minus 2L times the quantity of L squared plus x squared, the square root of that, plus L squared. So then moving these L squares together and then taking out the 1/2 kx squared, we get it's equal to 1/2 kx squared plus 1/2 kx times 2L squared minus 2L times the square root of L squared plus x squared. Then we could take out an L and a 2 from here. So that gets us 1/2 kx squared plus kl times L minus root x squared plus L squared. And then, because potential energies of a scalar, we could just add the potential energy from this spring and this spring. So it's just 2 times the potential energy of one spring, which is kx squared plus 2kl times L minus root x squared plus L squared.